Good. Got any new material?
I don't think so.
Is this Tuesday? I actually talked to your teacher today briefly.
Okay.
Sheila Kit, I guess is her name.
Yeah.
And she is going to send me a link tomorrow that will allow me to see exactly what the material is that you're covering.
Okay.
Okay? So we'll be able to stay on top of that a little bit better. I know we had one session last week where you and I went over a bunch of material that was not what you were covering. It's material that you're eventually going to need, but I think it gave the wrong impression to your teacher. So what do you want to do tonight?
It's more of what we did yesterday.
Okay. You read the problem, I'll write it, and we'll solve it.
Okay, it's a word problem.
Okay.
This is the volume in cubic feet of a CD holder can be expressed as V of X. V of X equals negative X cubed minus X squared plus 6X. Or, when factored, as the product of its three dimensions, the depth is expressed as 2 minus X. Assume that the height is greater than the width. And then it asks A, B, and C. A is factor the polynomial to find linear expressions for the height and the width. B is graph the function, finding the x-intercepts. What do they represent? C is describe a realistic domain for the function. And D is find the maximum volume of the CD holder.
Okay. Did I get this right? The depth is equal to 2 minus x?
Yeah.
Okay. Well, let's start by tackling this polynomial equation. What's the first thing we can do to it? A. Let's factor it.
Okay.
Okay? What's the first step of factoring it?
Pulling out your greatest common factor.
And what would that be?
X.
What's left over?
Negative X squared minus X plus 6.
Now, if I look at that, that's going to be tough to factor because there's a negative sign in front of the x squared. So what could we do to not have that?
I don't know.
What if we factored out a negative x instead?
Okay.
And that would make that positive, and this negative. And now, the reason I did that is because we're going to have to factor that, which factors rather easily, into what?
X minus 3.
Well, it's plus minus for sure. We need factors of 6 that subtract, because of the negative sign, to the coefficient of the middle term, which is 1. And then we want to put the bigger of those factors with the sign of the coefficient. So it's 3 and 2, because 3 and 2 subtract to 1, but the 3, the bigger factor, goes with the sign of the middle term. Notice why. It's because we need to produce a plus middle term. That's 3x, that's minus 2x. So that gives us that plus x. All right, so that's our factors. And let's see. Graph the x-intercept. Did I get that right? That is v of x, right?
Yeah.
What is v of x when this curve, whatever it looks like, is going to cross the x-axis? What is v of x when that happens? In other words, well, if I have a curve like that, every time it crosses the x-axis, what is v of x?
Odd.
0.
0.
You see why? In other words, the horizontal axis is the x-axis, but the vertical axis is v of x. So when you talk about x-intercepts of a function, you're saying basically, where is v of x equal to 0? Where is this thing right here equal to 0? Because that's what it is when I'm at that point, when I'm at that point, and when I'm at that point. V of x is 0. So the way we solve for those points is by setting v of x equal to 0. So if the problem now becomes 0 equals minus x times x plus 3 times x minus 2, what 3 solutions do you have for x?
1, minus 3, and plus 2.
The one that you got, in other words, the way I solve this equation is if I have the product of 3 things, which I do here, I have the product of that times that times that. If the product of 3 things is equal to 0, then each of those 3 things could be 0. And one of them has to be 0. That is the only way that you can get the product of 3 numbers to be equal to 0, is if one of them is 0. So the way we solve this is by setting each entity to 0. So my solutions are x equals 0 for this one, and your other 2 solutions were x equal minus 3 and x equal plus 2, correct?
Yeah.
Okay. So if I go on my x-axis here and I mark those 3 points, well, one of them is 0, and that's the x being equal to 0, not the y. But it does tell me that when x is equal to 0, y is equal to 0. I have another one at minus 3, and I have another one at 2. So this curve does do something like, this is what cubics tend to do. They have 2 local extrema, and in fact you can say that the most extrema that any polynomial has is is its degree minus 1. In other words, this is a third degree polynomial. That means that it can have at most two extrema here. This is a local maximum, this is a local minimum. But you know what I mean by that. In other words, if I had y equal x squared, it looks like this because it can only have one vertex. But a cubic function, which this is, can have two extrema. Now, when I drew this chart, I didn't know what the end behavior was. I just guessed. But if I look at the minus sign in front of the x cubed, I should have guessed that the end behavior is such that the curve looks more like this. Why? Tell me. Why does it look like this as opposed to this? Has to do with what we talked about last night. In other words, is the end behavior positive infinity? Is the left-hand end behavior positive infinity or negative infinity?
Negative.
Remember that the left-hand end behavior, you only look at that term, the highest degree polynomial, and we substitute negative infinity for x. So this becomes negative infinity raised to the third power. Well, what is negative infinity to the third power? Is it positive or negative?
It'd be negative.
Right. So this term is negative. Well, we still have that negative sign there, so now we have a negative times a negative, so it's plus. So the left end behavior is plus infinity, which means it has to come from this end. It can't come from the bottom. It can't come up from below the x-axis. It has to come down from above the x-axis. Merely looking at the end behavior, I can figure that out. And I can also figure out that when x goes to positive infinity, I've got v of x going to negative infinity. So this right side behavior also looks correct. So the left point of my graph, and I really shouldn't say it's a point because you understand this goes for forever without me drawing an arrow on it. The arrow isn't necessary. What happens is when we graph something like this, we graph it so that we look at the most important area of the graph, which is the area where it crosses the x-axis, where you have a local minimum, where you have a local maximum. That's the interesting part of the graph. So we don't really care what it does on the edges. In other words, we know this goes on and on and on, and this one goes on and on and on. So that's why we talk about end behavior. But in this case, the biggest reason to talk about end behavior is to figure out how to graph it. In other words, when I first looked at these three zeros, I knew the graph either looked like this or like this. Had to be one or the other. So to figure out which one, I merely have to look at end behavior. And the moment I realize that the left end behavior is plus infinity, then I know this is the way the graph looks. Okay?
Okay.
Part C. what is the effective domain? And let's go back a moment. This is the volume of a CD box. So if we want to look at these three things, we know volume is what? It's height times width times depth. Well, I've got the volume expressed as the product of three things. It makes an awful lot of sense to call these three things height, width, and depth. So what's the domain? The domain being all of the allowable values for x. What can x be here? Could x be... Remember that here's the graph of our function, and v of x has to be positive, doesn't it?
Yeah.
V of x can't be negative. Also can't be 0. So the only areas on this chart that are allowed are right there and right there. There's no way we can have an x that gives us a negative volume. Negative volumes don't exist. So when they say what is the effective domain, well, it would be what? X less than 3, less than minus 3, excuse me. You see that? You see why?
So that should be positive.
If x was somewhere between 0 and 3, we would have a negative volume. So we can't have an x between 0 and negative 3. If we have an x that is less than negative 3, then this part of the chart, that's positive volume. That's allowed. Or if we have an x between 0 and 2, we have positive volume. That's also allowed. Clearly, we cannot have an x between 0 and minus 3, otherwise we would have negative volume, and if we have an x greater than 2, we have negative volume. So our domain is x has to be less than minus 3, and also x can be greater than 0 or less than 2. Right there is your domain. Now, have you been taught how to give domain in interval notation?
No.
So this is the notation you use for domain, like I just circled there?
I guess.
Because there is a way to give domain in interval notation. Let me give you this in interval notation, and you tell me whether it looks familiar. X can go anywhere from minus infinity to minus 3, combined with from 0 to 2, and that's it. That's the domain right there. And notice that it can't even be minus 3, because if it was minus 3, the volume would be 0. And we know that we don't have CD containers that have a volume of 0. So x can't even be minus 3, it can't be 0, and it can't be 2. That's why I've used parentheses in the interval notation. And it's also why if I write it like that, I use less than signs, not less than or equal to signs. Still with me?
Yeah, I've never seen that before.
Okay. Well, let's not write it like that then. Let's write it like we did the first time, right here. X has to be less than minus 3, or X can be between 0 and 2. And you see from the chart why that has to be, right?
Can't have negative.
The horizontal axis is X. The vertical axis is the volume of this CD container. This chart, if you considered every point on the graph, there's points here where the volume is negative. Any X between 0 and minus 3 makes a negative volume. Also, any X greater than 2 makes a negative volume. So those aren't allowed. We clearly can't have X's that create negative volumes. And that's what they mean by the effective domain. If you just looked at this function, there is no restrictions on X. X can be all reals. It can be anywhere from negative infinity to positive infinity, if I look strictly at the function, v of x. But knowing that v of x is the volume of a CD container changes everything. It means that we have to have a positive volume. We can't deal with negative dimensions. We can't deal with negative, we can deal with a negative x value, because an x of minus 4 gives you a positive volume. We're on this side of the x-axis when x is minus 4. All right, let's deal with question D. What is the maximum volume of this CD container? Well, notice that if we look at this function that's factored, and we know that volume is height times width times depth, which it always is, then we can look at these three products and say, well, one of them is the height, one of them is the width, one of them is the depth. Notice that when x is negative, to a point, hold on a moment, let me think about this. The question is that how negative can we let x be? Because clearly, if we were able to let x equal minus infinity, that would give us the maximum v of x. You see why? In other words, the further we go to the left on the x-axis, which is what happens when we let x equal a big negative number, the higher v of x goes. So the maximum volume, if we could, would be to let x go to minus infinity. But there's a problem when x goes to minus infinity. And that is that, well, that's positive. but that's negative and that's negative. And if each of those is, if one of them is the depth, one of them is the height, and one of them is the width, we can't have any of that being negative. I'm thinking for a moment here. Well, clearly the maximum volume has to occur right there.
Okay.
Now I say clearly because
It's the only positive vertex.
well, it's not the only positive value of v of x. In other words, over here is higher. But x can't, well, and x is restricted. X is not going to be able to be what it needs to be for this value right there. We can't have an x of minus 5. Now, hold on, I'm slightly confused by this problem because this is interesting. The depth is equal to 2 minus x. Well, we have an x minus 2. So we could say that the negative of x minus 2 is 2 minus x. So this is the negative depth. That's minus d. Merely because they told us that d was equal to 2 minus x. Well, we're looking at an x minus 2, so that must be minus the depth, since x minus 2 is the negative of 2 minus x. We're also told that height is greater than width second. Are you supposed to be able to use a calculator on this problem?
No.
Let's see. I'm convinced that the maximum volume is in here, not over here. In other words, we need an x that is between 0 and 2. I would say that the maximum volume has to be the vertex of that quadratic right there. In other words, this point that we're coming up with is going to be the vertex of the quadratic. So to answer the question, the vertex of that quadratic is minus b over 2a, so it's minus 1 over 2. And if we plug that in, we get 1/4 minus 6. So I get 6, and I get a negative value. Oh, I meant to plug in negative 1/2. Which gives us minus b is minus 1 over positive 2, so doesn't make sense either. Well, I know it's 8:30. Let me think about this problem just a little bit more for tomorrow, and we'll finish it up tomorrow night.
Okay.
This is kind of an interesting problem that I haven't come across before. I got to straighten out what values will give me a positive depth, a positive width, and a positive height. And once I figure that out, I'm fairly certain that our maximum volume is going to be this peak right here. But
Okay.
at the moment, I can't quite figure out how to get it. All right?
Okay.
So let's pick it up tomorrow night.
Okay.
All right, Silas. Bye-bye.
Bye.